In this video, we will try to understand various physical layer waveforms in general, and then we will try to find out why cyclic prefix based OFDM waveform is used for the 5G new radio standard. Goals of this presentation are listed here. First of all, we want to understand the underlying motivations for understanding various waveforms. Then we will compare various waveforms which are discussed for 5G new radio, and in the end, in particular, we will compare the filtered OFDM with the cyclic prefix OFDM. So first of all, let us define what are the different use cases and the technologies involved in the 5G new radio. In regard to the use cases, first and foremost is the enhanced mobile broadband, and here we are addressing human-centric use cases. So these are related to the high data rate and large bandwidth. For example, access to high throughput multimedia content. The second is ultra reliable low latency communication. Here we have the strict requirement in terms of the latency and reliability. So we are talking about the use cases like connected cars, drones, and mobile robots. In a way, we are talking about two conflicting requirements, because we want low latency and high reliability. This makes the physical layer design, in particular waveform designs, complex. The third is the massive machine type communication, and we are talking about very large number of the connected devices. And then in terms of the technologies, there are massive MIMO and beamforming. So the number of antenna elements in the base station and devices are increasing, and we have the high frequency spectrum, for example millimeter wave. So keeping in mind the use cases and the technology involved, we need to understand the certain key performance indicator for a physical layer waveform. Let me start by saying that for any radio access technology, one of the deciding factor is its underlying waveform. For example, GSM uses Gaussian minimum shift keying, and it has a characteristic of the constant envelope, and which has its own advantages like excellent power efficiency and high spectral efficiency. Likewise, LT uses classic CP based cyclic prefix based OFDM waveform, and it has advantages like it is robust against frequency selective fading, the channel equalization is simpler. So if we define these performance indicators, there are some of them are listed here. First is the spectral characteristic of the waveform, and that can be further divided into spectral efficiency and spectral localization. So the waveform should be such that the spectrum is utilized fully. There is no waste of the spectrum. And localization can be further divided into two categories. One is time localization, another is frequency localization. For good time localization is required in order to enable the low latency, especially in a adaptive TDD system with the need of fast and flexible switching between the downlink and uplink. The waveform needs to enable this short switching time between downlink and uplink. Then another performance indicator is the multi-antenna support by the waveform. MIMO system depends on the knowledge of the channel or the channel state information. In the practical system, channel is not known to the receiver, so channel estimations are done. So the channel state information is not perfect. So it should be analyzed what is the impact of the imperfect channel state information on the performance. So for various physical layer waveforms, what is the impact on the performance because of the imperfection in the channel state information? It all also depend on the whether there is a cyclic prefix or needed or not needed in the underlying waveform, because that introduction of the cyclic prefix somehow reduces the interference, but in other way it also reduces the spectral efficiency. The third performance indicator is the power. So the waveform should not be power hungry. There should be low peak to average power ratio requirement. Also, the power amplifier linearization is a very important criteria, because in the real systems we have to consider the low cost design of the power amplifier which work in the power amplifier linear zone. The fourth is the complexity of the baseband system. So as we move forward the 5G radio access technology, the algorithms are becoming complex. So the underlying waveform itself should not add to those complexities. For example, the equalizer design in the receiver or in the transmitter complexity should not increase just because of the underlying waveform. The other performance indicator is the robustness against the RF impairment. For example, phase noise. So the low noise phase oscillators are costly, and therefore it is important the underlying waveform should have the robustness against phase noise and in general all the important RF impairments. The other important performance indicator is robustness against the synchronization error, for example time and frequency. So now based on this background, let's try to understand what is the underlying motivation to study other waveforms. The CP based or cyclic prefix based OFDM which is used in LTE today has certain drawbacks. First is that it has the high level of out of band emission. So in OFDM the shape of the used sync pulse in frequency domain results in the out of band emission, which causes strong interference into neighboring frequency bands. And if we see the 5G use cases like massive machine type communication and ultra reliable low latency communication systems are impacted by this drawback. The other thing is the one of the requirement is that we minimize the leakage of the power outside the very narrow guard band around the useful signal band. But in OFDM there are large side lobes which causes to reduce the spectral confinement and also reduces the occupied bandwidth. For example, in LTE the maximum occupied bandwidth is 90% of the allocated channel bandwidth. So if you have 20 MHz channel, only 100 RBs are used, which is the 90% of the allocated possibly allocated channel bandwidth. This is also again impacts the mMTC and ultra reliable low latency communication use cases of 5G. Third is the sensitivity to the carrier frequency offset and long round trip delay time. So if you are talking about low latency systems, and if the waveform itself has a long round trip time and it is sensitive to carrier frequency offset, then it impacts both the use cases, which is ultra reliable low latency communication and enhanced mobile broadband. The fourth and important is that CP based OFDM waveform has high peak to average power ratio. So it becomes very difficult to design cost-effective power amplifier, especially for massive MIMO system, and it affects or impacts most of the 5G new radio use cases, which is ultra reliable low latency communication, enhanced mobile broadband, and massive machine type communication. With this knowledge, let's try to understand the cyclic prefix based OFDM signals drawback using this web demo, which is available at the website of the University of Stuttgart. In this web demo, we can define the number of subcarriers, length of the CP, and we can plot in three different ways. We can plot PRB wise, in which we can define number of subcarriers within PRB and number of PRBs. Subcarrier wise plot, we can define number of subcarriers, and for allocation wise plot, we can define number of allocated subcarriers. For plot itself, we can plot in time domain, frequency domain, or both. So maybe we'll stick to frequency domain for this demo. Okay, maybe we'll plot subcarrier wise, and I will give only 2 subcarriers. Define CP length of 100 samples. So now we can see that this is the representation of the OFDM signal in frequency domain. The subcarriers, I have taken 2 number of subcarriers, so these are closely spaced subcarriers and they are overlapping with each other. But that is not a problem because these subcarriers are orthogonal, which means that if we see 2 adjacent subcarriers, in this case there are 2, only 2, and this red one and this blue one. These are the peaks of the subcarriers, and the peak of this subcarrier is aligned with the null of the adjacent subcarrier, which means they are orthogonal and there is no intercarrier interference. The subcarriers will interfere with each other only if there is a loss of orthogonality. For example, if there is a frequency error, that will cause the subcarrier frequencies to shift, and in that case the peak of this subcarrier will not align with the null of this subcarrier, and this will result in the loss of orthogonality, and it will result in the inter-subcarrier interference, and this is one of the drawback of the cyclic prefix based OFDM. Also, another drawback which we saw is that the cyclic prefix OFDM has a large number of side lobes. So these are the side lobes, and these are the main lobes. So this is again a drawback because we don't want to leak the spectral power. Now let's look at some of the examples of 5G NR waveform which were analyzed. So some of them are listed here. Mainly there are 4 waveforms. First is obviously the classic CP based OFDM waveform, which is used today in LT system. And if you look closely, all the waveforms are related to the filtering. Only difference is how and where that filtering is applied. So in case of CP based OFDM waveform, the rectangular filter is used, and that filter spans over total number of subcarriers. In case of generalized frequency division multiplexing, there is a pulse shaping filter is used, and this filter is applied or spans over per subcarrier. In universally filtered multicarrier waveform, the filtering is applied over a band of subcarriers. So the multiple subcarriers form a band, and over which this filtering is applied. In filter bank multicarrier waveform, the polyphase filter banks are used for pulse shaping, and filtering is applied per subcarrier basis. So if we see the comparison of these waveforms, which I have taken this table from this IEEE paper, and it summarizes the differences between these waveforms. For example, in case of OFDM waveform, the filter granularity is whole band, and the length of the filter is also an important factor, which is generally less than equal to CP length in case of OFDM. And OFDM signal is orthogonal in time and frequency, but it has a problem of out of band emission. Then there is a generalized frequency division multiplexing, where the filter granularity is over subcarriers instead of whole band. Here the filtering spans over subcarriers, and the filter length is more than the less than equal to CP length. Here the filter length is greater than symbol duration, and we are talking about completely different kind of waveform, where the waveform is non-orthogonal in time and frequency. But one advantage of using this waveform is that out of band emission is good, which means there is not much out of band emission. Other is the filter bank multicarrier waveform, where the filter granularity is subcarrier wise, but the filter length is increased, sometimes more than 3 or 4 times symbol duration, and these are orthogonal in real domain only. But best part is that the out of band emission is best in this case. There is a universally filtered multicarrier waveform, in which case also the filter granularity is sub-band, and this has shortest filter length, so it is equal to the CP length. These are orthogonal in the time domain and quasi-orthogonal in the frequency domain, and the out of band emission is good. Then there is another class of waveform which is called filtered OFDM, in which case the filter granularity is sub-band, and the filter length is still high. It's around less than equal to half of the symbol duration. It is again in time domain it's non-orthogonal and quasi-orthogonal in frequency domain, and it has a good out of band emission. This is another way of looking at the comparison among various waveforms. These are probably the performance indicators we actually saw earlier. For example, there is a peak to average power ratio, which is very high in case of CP-OFDM, and it is moderate in case of generalized frequency division multiplexing. Similarly, the spectral efficiency, which is very low in case of the CP-OFDM, and it is very high in all other cases. Overhead in terms of the adding CP, it is high in CP-OFDM. FBMC doesn't require any CP, so there's a low overhead. Similarly, in the case of GFDM, shorter length of the CP is required, so there is a variable overhead. Also, UFMC doesn't require CP, so the overhead is low. Out of band emission we already saw. The computational complexity is another important factor, and which is very low in case of the OFDM, and all other cases it is high. Other equalization is same, revolves around the complexity, which is simple in case of the cyclic prefix OFDM, but it is very involved in case of filter bank multi-carrier waveforms. And resource allocation is dynamic and fine-grained in cyclic prefix OFDM, and it can be configured in all other cases. One other important factor is short bus traffic, which is required for the machine type communications or ultra low latency type of communication, which is not there in the CP based OFDM waveforms, and also in the case of filter bank multi-carrier waveforms, but it is there in generalized frequency division multiplexing and universally filtered multi-carrier schemes. And fragmented spectrum, in CP-OFDM there is no fragmented spectrum. In all other cases there is a fragmented spectrum. Layer 1 latency is also high in CP based OFDM and FBMC case. It is moderate in case of GFDM, and UFMC case it is very low. If we see all these comparisons, this one and this slide, we see that there is no clear winner. In some cases, for example, spectral efficiency is low in CP-OFDM, and FBMC all other cases high, but the complexity is high in all other cases, but CP-OFDM has a low complexity. So there's no clear winner in all these waveforms. So keeping in this mind, 3GPP has chosen CP based AFDM for the release 15 candidate, and in August 2016 it agreed to adopt CP-OFDM for both uplink and downlink in 5G. Also, one important thing to note that CP based OFDM waveform was used in LT only in the downlink direction, but now it will be used in both uplink and downlink direction, so it will play a greater role in 5G neo radio compared to the 4G LT. Okay, now let's see this comparison a little bit. For example, here the same website from the University of Stuttgart compares the filter bank multi-carrier waveform, a class of that kind of waveform versus the classical OFDM. And we can see here, if I compare this only in frequency domain with the OFDM, yeah, we can see that the maybe just the subcarrier wise plot, and maybe I will have only two. Yeah, so here we can see that the roll off is very quick in case of the FBMC, and in case of the OFDM the roll off is not very quick, and that makes a good amount of difference in so this is it all about the 5G waveforms and how the selection was done. We didn't go through the entire details of the each scheme, but we just wanted to compare all the waveforms. That was the intention of this presentation, and thank you for watching.